Well, hello, honors, and as it turns out, AP, you're going to be watching this one too, so we're both watching this one. This is going to be a video on friction. We finally made it to talking about friction. Friction is one of those things you'll see as we go on through the year that is going to be in the way. It's something we're going to want to reduce and minimize, but at the same time, it's that friction that we want rid of that makes motion at all even possible. So there you have it. There's two types of friction we're going to talk about. We're going to talk about kinetic friction. We'll talk about kinetic friction. And we will also talk about static friction. So we'll talk about kinetic friction and static friction. Kinetic friction, we're going to use the symbol lowercase f, subscript k, and for static friction, lowercase f, subscript s. Both friction forces are forces. That was a weird way to say that. Whether it be kinetic or static, friction is a force, so we'll treat it like a force. Okay? And like all forces, well, we'll see. I'll continue on with that in a minute. So, first I'm going to talk about kinetic friction. So looking at kinetic first, okay? So kinetic friction. The force of kinetic friction is equal to the Greek letter mu, subscript k, and capital N. Now let's unpack this. The force is equal to the Greek letter mu, subscript k, times N. N, to remind you, is our normal force. So normal force, well, if you imagine something sitting on a table, there's a thing sitting on a table, you know that gravity's pulling that thing downward, and at the same time you know the table's pushing upward on it. So that would be the force from the table. Well, normal force is just a fancy name for when a surface, in this example the surface is the table, pushes back. So this table, a surface, is pushing on this thing, this box, we'd call that a normal force. So the force from the table, normal force, is just a fancy name for it. It's just the name we give to the force a surface exerts, and the reason they use the word normal is mathematically normal means perpendicular. So mathematically normal means perpendicular, and if you think about it, this table is not going to be pushing at some weird angle. It's going to push perpendicular to its surface. Okay? So generic name for that force would be the normal force. Okay? Now that brings us to mu. Mu is called the coefficient of kinetic friction. So this is a coefficient of friction, and kinetic because we're talking about kinetic friction. Coefficient, well, that just means it's just a number, it's a constant, but it's a material dependent constant. So for example, if you had rubber rubbing against glass, you'd have one particular coefficient of friction. If you had rubber dragging across concrete, you'd end up with a different coefficient of friction. If you had concrete dragging across glass, you'd have yet another coefficient. So the coefficient is just a number determined by what two materials are rubbing up against each other. And that is a number that you can look up in a table in your textbook. And when we do a problem in class, I'll show you where those tables are. Okay, so we got a constant and a force. So that's what kinetic friction. Kinetic friction is the friction involved in things moving. Kinetic is just another word for motion. So for kinetic friction, the way you'd visualize that, say, is we'll go back to our table example. Here's some box on a table. Let's say I pull on it that way with some force. Well, there's going to be friction associated with that. Friction is going to be in opposition to the motion. This is now something that we're going to say is going to accelerate that way, so this thing is clearly moving to the right. That force is big enough to exceed friction, but friction is going to oppose it. Right? So friction is always working against you. So motions to the right, friction is going to be a force to the left. And if I wanted to write down Newton's equation for this one, for this example, I would say, for just looking at the x direction part, I would say the net force would equal ma. The net force in this case would be force, and in the negative direction we'd have friction, and that would equal ma. And from this point, we'll do problems in class, but at this point we would start playing around with that equation and solving it for something. But just trying to show you how this works. Friction is a force that's opposing us, okay? Now, that's kinetic friction. The other one we want to talk about is static friction. So let's look now at static friction. Okay, static friction. Well, the equation for static friction is going to be lowercase f subscript s for static, and as it turns out, that is not equal to, it actually turns out to be less than or equal to a coefficient times a normal force. Well, again, this coefficient is the coefficient, it's now the coefficient of static friction as opposed to the coefficient of kinetic friction. Static means not moving, so we're now talking about friction involving things that are not moving. We're static. And this coefficient is again materials dependent. If you have a piece of rubber sitting on a piece of glass, you have a piece of rubber sitting on a piece of concrete, whatever the two materials are will tell you the coefficient. That's a number we can look up in a table in our textbook, and once again, when we get to solving problems, I'll show you where those tables are. But this is just a constant. The thing that makes static friction, other than the fact that static friction is friction associated with not moving, and kinetic friction is friction associated with stuff that is moving, the other big difference is this inequality. Now, in our class, we're going to be dealing with situations where this inequality is going to be an equality. But for now, the static friction has to be less than or equal to this value. And the reason for it is this. I'll talk about this for a few moments here. But if you imagine, say, here's the ground, here's some box on the ground, and nobody's doing anything to it. So if the force of static friction was at its maximum value, right now the force of static friction is 0 because clearly this box is just sitting there. We're not accelerating, meaning net force on it is 0, so it's just sitting there. So the force of static friction has to be 0. Now, if I applied a small force to this, you can do this right now, touch your iPad and push on it very, very gently. And if you push on it very gently, you'll notice it doesn't start moving. That's because you're pushing on it gently that way, and the force of static friction has now increased to stop you from moving it. And because you have a force and a force opposing it, the net force still adds up to 0, and the static friction is not doing anything. If you push harder and harder and harder, if I push harder, the force of static friction will grow as well. Eventually, though, if you keep pushing harder and harder and harder, eventually what will happen is this will become so big that it actually becomes greater than the maximum of this, and in this case we would say that we've reached the maximum value of static friction, and the force of static friction would be equal to mu times normal force. Now, how do I know this is the case? Well, if the force of static friction was always at its maximum value, then if I stopped pushing, a box wouldn't be able to just sit there. If the force of static friction was at its maximum value all the time, as soon as I stopped pushing the box and let go, it wouldn't stay there. It would take off this way. We've got this force on it, that box would go flying off to the left. It isn't, because the force of static friction actually changes. I admit that is a very weird concept, but it is how it is. Well, I've prepared a short little video for you to watch so you can see this in demonstration. Barely touching it, pushing harder, 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 it breaks free and it starts to move. Okay, it's just sitting there, barely touching it, more, it breaks free and starts to move. The force of static friction grew in value until it was no longer able to stop me from moving it, at which point I won and the cup started moving. However, when I stopped pushing, the cup stopped moving. That means the force of static friction shrunk all the way back down to 0 again. Alright, I hope that makes some sort of sense. As far as I can tell, that's all we really need to talk about friction. I think we need to start doing some problems. So when we're done with this, we'll do some problems up at the whiteboard. We'll